Okay, so good afternoon, everyone. Welcome back. Today, till now, we have discussed about the classical estimation theory and classical hypothesis testing. All right. So now we will discuss how we need the Bayesian estimation theory instead of the classical estimation theory. Why we do need it? All right. So in that one, the first problem that arises here. So what does the basically p value really means here? So in the p value, what is the confusion that arises? That p value is basically probability that data given h naught, but what really we want that is the probability that h naught given data, and both of them are not same. So we understand it by the following example. We just take the example of medical screening paradox. So here we just assume that we take a diagnostic test that is 99% sensitive. All right, that is 99% sensitive and 99% specific. Okay, means detect the disease when it is present 99%, and 99% it is very specific that negative when disease is absent. So in that one, your suppose our test is positive, all right, and with the disease prevalence that is 1 in 10,000. So what is the probability that actually we have the disease? So many people will say by saying this one is 99%. Okay, many people institute that 99% because of the test is so accurate, but the correct answer from the Bayes theorem is about only 1%. Okay, that is the correct one in the reality. How? If we just go to the screening paradox in the mathematics by that one, let d is the has the digits and plus is denoting that the positive test. So how you will find that? So actual what we need to find out, we need to find out that the probability that you have the digits where the test was positive. All right. Given that the test was positive, so in that one, it will be that it will be equal to the probability that test was positive, given that you have the disease into probability that patient has the disease divided by the probability of positive test. All right. So we will expand it. So in that one, by the Bayes theorem, it will become probability that test was positive, given that disease was there. All right, into probability of disease present divided by the probability that test was positive, given that disease patient has the disease, into probability that the probability of patient has the disease plus probability test was positive, given that patient doesn't have the disease, into probability that patient doesn't have the disease. So that will be 0.99 into 0.0001, because that is the uh, your prevalence in your test, divided by 0.99 into 0.001 into 0.01, because that is the chances that you have the test positive when patient doesn't have the disease, into 0.9999 is the probability. When you are going to solve this one, it will be equivalent to the 0.0098, that is almost 1%. All right. So the prior probability matters and classical statistics ignore it. All right. So that is the one most important thing. In the classical estimation theory, we ignore the prior information. All right. For example, when we are driving the car, in driving the car, while we are looking in the front So that is our experimental data. So if you don't have the side mirrors and the back mirrors, so at that time you will just have to look at on the front side. So that is your experimental data, and at that time the chances of the accident is quite high in compared to when you have the side mirrors and the back mirror in your car. So in the classical estimation theory, you have the only experimental data. Means while you are driving a car, so you are looking at the front side, that is your experimental data. So means you are driving with the classical estimation theory, but when you have the side mirrors, so you have the extra information or prior information who is coming from your left, who is coming your from right, and who are in your back through the back mirror. So at that time, the chances of the accident will be very low in compared to the situation when you don't have the side mirrors and the back mirrors. So means the accuracy will increase. So in the Bayesian estimation theory, the accuracy of the estimates will increase because you will have the prior information. All right. So the second problem occurs here in the classical estimation theory, classical hypothesis interval estimation. The classical view says that if we repeat the experiment infinitely, 95% of the intervals would contain theta. But for the specific interval, theta is either in it or not. And the Bayesian view, for the given data, there is a 95% probability that theta will lie in the interval. Okay, that is the actual thing we want. All right, for example, in the weather forecast analogy, what is the statement in the classical estimation theory? It will be in the similar condition, it rains 75% of the time. But in the Bayesian, what should be our statement? It should be given today's condition, there is a 70% chances of the rain. That is the basically difference between classical estimation theory and the Bayesian estimation theory. All right. Second thing is that problem in the classical estimation theory is that cannot incorporate the prior knowledge. In the classical statistics, treat each experiment in isolation, ignore the domain expertise and the previous studies. All right, and the parameters theta is fixed but unknown. All right. For example, here we are going to take the example of drug dosage studies. So we take the scenario of testing the optimal dosage of the new drugs. So what should be the prior information there? The similar drug worked at the 50 to 100 mg. The toxicity increases above 150 mg, right? And the year of the pharmacological research that they took, that are the prior knowledge for us for such kind of drug testing. Okay, drug dosage testing. But in the classical estimation theory, we don't include all these things. In the classical approach, we ignore all these and treat all the disease equally likely. All right, but in the Bayesian approach, incorporate these knowledges into the prior. For example, another example we just take, uh, if someone has the fever, so when you just go to the doctor to treat for the treatment of your fever, if the doctor just check your temperature, body temperature, and after that, doctor just provide you the medicine based on the your body temperature. So that is your basically classical estimation theory. Means you have he has the experimental data that is your body temperature right now. Okay, and based on that he's providing you the medicine and the treatment. But if the doctor asks you, and the mostly doctor do that, what he asks you that from how many days you have the fever. Okay, from how many days you are feeling the fever. So most of the doctors ask this. Why they ask this? Because they want to gather the prior information, the additional information from you. So if they have the after that they will check your temperature, body temperature, and after checking your body temperature, they will incorporate that prior information that from how many days you have the fever, and accordingly he will give you the treatment. So now the question arises that if he doctor doesn't ask you that from how many days you have the fever. So at that time, doctor will consider that you have the fever from today itself only, right? So he will give you the medicine accordingly. So in that situation, what will happen? It will not be that much effective, correct? But if you just tell the doctor and doctor asks you that from how many days you have the fever, and you tell that I am feeling the fever from last 2 days or 3 days, so at that time what will happen? Definitely, he will change the medicine and he will give you the medicine accordingly, and that will affect in a much better way. Correct. So that is the Bayesian inference from your daily life situation in compared to the classical estimation theory. Second is that sample size and stopping rule. So in the classical testing, the p-value depends on the data you collected. Okay, and the data you might have collected but didn't you have. All right, so for example, collect the exactly 100 sample, then test, and plan B is the collect sample until you have the p less than 0.05 or n is equals to 100. So same final data is different from the different p values at that time. All right. So in the Bayesian inference, what is the advantage that you have? The Bayesian inference depends only on the observed data, not on the sampling plan, right? So that is basically the probability theta given data proportional to the probability that data given theta into p theta, right? So how the Bayesian philosophy work in the fundamental difference here in the statistical way, that theta is fixed in the classical estimation theory and data is random. In Bayesian, theta is random and data updates our belief about the theta. All right. So here, based on the Bayes theorem, you have the prior belief that is your pi theta, the information about the theta parameter theta. With respect to that, you have the collected data that is your x1, x2, xn, and then based on that you just collect the posterior belief that is your posterior distribution that is your pi theta given x. So today's posterior is tomorrow's prior. That means whatever the information you are collecting today means, if we just carry forward with that example of the doctor and patient, when you just tell the doctor that I am having the fever from last 4 or 5 days, so that is your prior information. Okay, and the doctor is going to measure your temperature, body temperature, that is your x1, x2, xn. Okay, your sample data, and after having both of them, okay, prior belief and data, you have the posterior right now. So when next day you will go to the doctor, and again doctor will check your body temperature. So whatever the data x1, x2 he will collect. So by multiplying with not only multiplying, by including the prior belief and yesterday's data, now your posterior will change. Okay, so that's why we are saying today's posterior is tomorrow's prior. Okay, so this is your posterior, basically pi theta given x curve, and the likelihood function equals to fx theta given theta, that is your likelihood, and pi theta is your prior, divided by f integral over the range of theta of fx given theta into pi theta. That is basically your marginal likelihood. Okay, normalize, and we sometimes we call it as the normalizing constant. All right. So that is your Bayesian inference. That's how we use the Bayesian inference. And other things we will discuss what is the type of priors. We have the different type of priors, that is basically informative priors, non-informative priors, weakly informative, or conjugate priors. These are the priors that we discuss in the future lectures. And if you want, you can go to the YouTube and you will find out my lecture 1 about the Bayesian inference. All right, all the things you will find there only. All right, and we discussed there the conjugate priors and the Bayes point estimation techniques. We discuss under the different type of Bayesian estimation, means under the self, under the ALF under the line X and other things, and similarly we discussed the credible intervals. All right, so how it is different from the, here we will discuss how it is different from the that one. Okay, so in the credible interval, that this is the probability that your theta will lie between the limit, lower limit L and upper limit U for given data set. The probability is equals to 1 minus alpha, means given data there is a 1 minus alpha probability that theta will lie between L and U, that we actually want. In the confidence interval in the classical estimation theory, if we repeat 1 minus alpha of the intervals contain theta, interpretation that we are 1 minus alpha confident in our method. Okay, for this specific interval, theta is either in it or not. All right, and the type of credible interval equally tailed where alpha by 2 the probability for each tail, and second is the highest posterior density, that is the shortest interval containing 1 minus alpha probability. Right, that is your basically the introduction of your Bayesian inference, why we need the Bayesian inference instead of the classical estimation theory. Okay, thank you.